So now let's go ahead and try to do one 2's complement multiplication. Okay, let's say I want to do minus 3 into minus 5. Okay, so before that, if I have an n bit 2's complement number, what is the range of this representation? Yeah? Yeah. So this will lie between minus 2 power n minus 1 to 2 power n minus. You're saying this. Okay, what are the values corresponding to this, the bit binary representations? Minus 2 power n minus 1 is what? 1, 0, 0, 0, 0, all the way. What is this representation? 0, 1, 1, 1, 1, 1. Okay, correct. Right? So for minus 3 and minus 5, how many bits, minimum number of bits do we need to represent this? 4 bits, right? So therefore we can write this as what? 1, 1, 0, 1, and this is going to be 1, 0, 1, 1. Okay, so let's go ahead and do this number multiplication and see. So we go ahead and do it as we did earlier. The first partial product will be 1, 1, 0, 1. Second partial product will be shifted again, but the same number, right? 1, 0, 1, 1. What about the third one? All zeros. So this will just be 0, 0, 0, 0. Fourth one, yeah? 1, 0, so 1, 1, 0, 1. 1, 0, 1, 1, right? So can you now add these numbers and tell me what you get? What are you supposed to get eventually, by the way? Minus? Minus, plus 15, right? This has to be plus 15. What is the representation for plus 15? Yeah, very important. Plus 15 has to be 0, 1, 1, 1. Don't say 1, 1, 1, 1, 1. 4 ones is equal to what? Minus 1 in 2's complement representation. So you cannot leave this preceding 0 out when you're dealing with 2's complement numbers. So you have to get 0, 1, 1, 1, 1 as your answer. So do it and now tell me if you are able to get it or not. So is this right? Yeah? So is it right to discard the carry? Yeah? Okay. So first thing is, when you're doing 2's complement multiplication, you have to be very careful about, like I told you, about the preceding 0. That will change the value completely. So therefore, to say that this is the first partial product is equal to 0, 0, 0, is it right? What should I do? You have to do what is known as sign extension, right? You have to do sign extension to get this right. So first thing is, we'll look at that. Sign extension of 2's complement numbers. Let's say I have a representation an minus 1 a naught, right? A naught equals minus 2 power n minus 1 a n minus 1 plus summation k equal to 0 to n minus 2 a k 2 power k, right? Now what am I doing? What is sign extension? It's taking this a n minus 1 bit and repeating it k times, okay, or repeating it m times. Okay, I'm going to create a new number which is sign extended a. So what is that value? It is a n minus 1 all the way to a naught, and I'm going to repeat this guy a n minus 1 a n minus 1 all the way. How many times? I'm going to sign extend it by m bits. So by sign extending it m times, this now becomes a how many bit number? M plus n bit number, right? So this guy, if you look at overall, it's an m plus n bit number. Okay, so now what I'm going to do is, I'm going to simply show that this m plus n bit number is exactly equal to this in value. So if this is an m plus n bit 2's complement number, what is the value? Minus 2 power m plus n minus 1 into a n minus 1 plus 2 power m plus n minus 2 a n minus 1. It's the same bit all the way down to what? 2 power m, no, n a n minus 1, right? This is my sign extended value plus the old sum now, not the old sum. Remember now a n minus 1 will get multiplied by plus 2 power n minus 1 now, plus 2 power n minus 1 a n minus 1 plus the remaining part of the sum, k equals 0 to n minus 2. Let me put that on the next line. Okay. Plus summation k equal to 0 to n minus 2 a k 2 power k. Now can you take a n minus 1 out common, right, and show that that previous guy reduces to the can you show that this term value is nothing but this guy? So just take an minus 1 common and minus 2 power n minus 1 out from here. This term I'm going to write it as minus 2 power n minus 1 an minus 1 into the remaining terms, that is plus 2 power m minus 2 power m minus 1 minus 2 power m minus 2 all the way down to what? Minus 1. What is this summation equal to? This summation is 2 power m minus 1, right? Therefore, we will get minus 2 power n minus 1 an minus 1 into 2 power m minus 2 power m minus 1, which is nothing but minus 2 power n minus 1 an minus 1. Right? Therefore, sign extension of 2's complement numbers does not alter the value. Okay? So now let's go back and do the same example that we did by correcting for the sign extension. Okay? So we had what? Minus 5 into minus 3, is it? What is it? Or minus 3 into minus 5? Minus 3 into minus 5. Or let me just go back here and correct it. Okay? So the sign extended bits are now like this, right? For this also it's going to be like this. This will be 0. What about this last term here? Is this correct? Okay, now do the addition. Tell me what you get. 1, 1, 1, 1, 1, right? 0, 1. Isn't this what you get? What went wrong? Sign extend the sign extend, or you have to consider the sign of the multiplicand. In the sense, this last partial product, this guy, we said is 1101 because we are multiplying with a 1 there. But that's actually a minus 1. See, this number here is minus 2 power 3 plus something. So when I am multiplying by the MSB alone, it's actually a negative number. And therefore, what I have to put here is not just that value, but the negative value of that guy. Right? So if I get minus 5, I have to put plus 5 there. Right? Oh no, minus 3 into minus 1, I have to put plus 3. So this has to be 1100. Correct? Now what do you get? I add 1 here, I get 1 here, 1 plus 3, 1. So 1, I get a, let me put the carries in a different color. Okay? So I get a carry of 1 here because I am adding these 3 ones. 1, 1. Now I add 4 ones. What do I get? 0. Right? And the carry will go where? Here. Right? Now what do I get here? 1 plus 1? 0. I get a carry of 1 here. Now again I get 4 ones. Okay. So I get 0. Okay. Now this is a very critical and a very subtle point that you have to follow. I can sign extend these numbers to how many ever bits I want, and yet my answer should be consistent. So if I tell you that the answer is 0, 1, 1, 1, or 0 followed by 4 ones, or 0, 0, 0, 0 followed by 4 ones, or any number of zeros followed by 4 ones, the answer is still plus 15. The arithmetic should be such that how many ever bits I sign extend, I still get that answer. Previously we said we have to drop that carry. That is not correct. The carry is going to be used in order to allow this sign extension to as many bits as you want. You get it? So now, for example, here, if I sign extended this further, right, 0 and then put another 0 here, then this carry would still do the same thing, will give me 4 ones, 2 ones, get me all zeros there. This is a very subtle point. Go back, look at the arithmetic that we did here, look at the arithmetic, the mistake that we made earlier. The carry cannot be dropped, or the carry is not the MSB of your 2's complement multiplication. The carry is going to enable sign extension to as many bits as you want. Which means, if I give you 2 unsigned numbers and say, how many bits is the final answer? It is m plus n minus 1. No problem. If I give you 2's complement number and ask how many bits should the final answer be, of course it needs a minimum number of bits. But beyond that, I will reverse the question. I will say, you tell me how many bits you want. I will perform carry propagation until you get the number of bits that you want. You understand, this question in 2's complement itself becomes meaningless beyond the minimum number of bits, that is. Okay, please go back, work out. Yeah, correct. Yeah, so carry will go to 2 bits away. Yeah. So that's what I'm saying. You work out this example for more sign extension. You will see that the same 4-2 pattern will keep repeating. And it will ensure that these preceding values will always be zeros, whatever you do. That final carry will be 1. Nothing can be done. So you tell me how many bits you want. I will truncate and give you, because that's all you need. The carry I will just discard at that point. Yeah. Why are we doing only in the? Correct. Oh, that's because you look at the mathematical representation, right? This is, if you take this 1101, 1011, this is basically minus 2 power 3 plus 2 power 1 plus 2 power 0. And we are now multiplying with this number, right? Let's say this is x into this. So if I write this, it will be minus 2 power 3x plus 2 power 1x plus 2 power 0x. That's what we are doing here. Wherever there is a plus, we retain x as it is, right? 2 power 1x means we are shifting by 1 and retaining x as it is. Wherever there is a minus sign, I am absorbing this minus into x here. It will become minus x into 2 power 3, and therefore I am shifting by 3 bits and putting minus x there. So if you want me to label this, the partial products will be x into 2 power 1 minus x into 2 power 3. That's how you are achieving this. Okay, clear? That's why I am doing the math here, because only then you can be convinced of some of these subtle points.